excuse me. So the second part of the session is going to be about set theory. All right. So we'll talk about the ideas of set theory, the concepts of set theory that you will need to use in further proofs and everything related to set theories later on, and in other concepts as well that we'll discuss later on. You'll use the concepts of set theory to prove other things, and in algorithms as well later on you'll see that you'll use concept of set theory. In fact, you have already used concept of set theory in your previous courses with or without realizing them. So let's get started. First, we'll start with the definition of a set. A set is any well-defined, unordered collection of objects. All right, well-defined, unordered collection, the keywords. First of all, you have to define it. Also, you have to know that it can be unordered. That is, the order doesn't matter, and it's a collection of objects. For example, your class, this entire class of students, this is a collection of objects as well. This is a collection of objects, and this is a set. This is a set of the students who are taking discrete mathematics in the autumn semester in the year 2020 in section 3, right? So what have I done just now? I have defined the collection. So you see, well-defined collection of objects. So this is a set. And when I talk about this as a set, when I address you guys as a set, think of that as a list of all the people. Now in that list, if that's the set, now if I rearrange the order in that list, there is a certain order there, right? If I rearrange it, does it become a new set? No, it doesn't, because the keywords and unordered. So a set is any collection of objects that is well defined and unordered. That is, order does not matter. Okay. All right. So elements of a set. Elements of a set are all the objects that make up a set. In the set we just defined for this class, what are you guys? You guys are all the elements of that set, the objects that make up the set. How do we denote an element of a set in set theory? We use this symbol here, this symbol that you see. Say this capital A is a set. This lowercase a is an element. We say that this A belongs to the set A by using this symbol. All right. If you have this symbol, it means that this lowercase a, this element A, belongs to the set A. Okay, that is what it means. Or this A is a member of the set A. If there's a certain element or a certain object wherever which does not belong to a certain set, any object that does not belong to a certain set, we represent that by this symbol. The same symbol actually by a hatch across it or crossed out. All right. The same symbol just crossed out represents the fact that A is not an element of A, of the set A, or A does not belong to the set A, or A is not a member of the set A. All right. So that is how we represent the idea of an element of a set. How can a set be represented? It can be represented as a list. For example, your set, the set of this class, can be represented with curly braces on two sides and the names of all of you, the names of all of the students listed out, separated by commas. All right, as simple as that. We can have it in the curly braces and the names of all of the students separated by commas. That's all. For example, here, the one that you see, a set of the numbers 0, 2, 4, 6 can be represented as a list in this manner. Curly braces on two sides and the numbers inside separated by commas. All right. Here as well, this is another example of the set of all even integers. By looking at this list, we should be able to tell that this is a set of all integers, even integers. Why? If you look at that list, this list, we have curly braces first of all. So this is a set. The curly braces are there, means what? This is a set. And the numbers inside, if you look at them, we see that there are negative integers here. There are positive integers here. There are no fractions or anything, only integers, but negative, positive, 0, all of them are here. However, all of them are even. So by looking at this, we should be able to tell that there is a pattern. What is the pattern? The pattern is that all of them are even integers. And what are these dot dots to the left and the right? It means that numbers, all the even integers preceding -6, all the even integers after +6 are also there. All right. So the dot dots represent that continuation, basically. Continuation from before, continuation after on both sides, basically. So yeah, this is how you can list the elements of a set. For a finite set like this, where you have limited amount of elements, for an infinite set like this, with dot dot on two sides and a list of numbers that represent the pattern. Now, if we were to represent the set of this class in this way as a list, do you see a problem with that?
I just didn't get the question.
Do you see, first you understand how we can list sets like this, right?
Yes.
We can represent sets like this. If we represented the set of this class, your class, in this manner, do you see any problem with that? Would there be a
Yeah,
potential
ma'am.
from that?
If the list is long, then the set will take too much place to write.
It's going to be way too long or way too big. The representation will be too big, in other words, right?
Yes, ma'am.
Yeah. Okay. Now, okay. Even then, still you list it out somehow. What if I was talking about the set of all students, all current students of IUB, of all current students of IUB? What would you do then? Even more inconvenient, right? What if I were to talk about all students of IUB, past, present, whatever? Even more inconvenient. So how do you list it out? It's not possible. For that, we have the set builder notation. In the set builder notation, we go by definition. All we do is we just define the characteristics that are required in order to belong to the set. So the set still is on the boundary represented with curly braces, that you have curly braces on two sides, and we use a predicate or a propositional function to define the characteristics that an element must have in order to belong to that set. All right. So as you can see here, x such that px. What does that mean? This x will belong to this set only if px is true. The set of all x such that px. You can either use colon or use this vertical line or this vertical partition, whichever. Any of these two. Either one of these two notations are used to separate between the variable that represents the elements and the predicate. All right. And what it means is that this variable represents all elements of the set such that px, such that the predicate, that is such that the characteristics are fulfilled. All elements which have this characteristic that is stated in the predicate will be a member of this set. For example, here, what do we have? X such that x is an even integer. This part is an even integer. What is this? This part on the right-hand side is an even integer. What is this? Predicate. This is the predicate. In other words, this is the definition of the element, or this is the characteristic that the element must have in order to belong to this set. X such that x is an even integer. If x is an even integer, x will belong to this set. As simple as that. Another way of saying the same thing is here. All right. Here you see in the predicate, we're only saying that x is even. We did not mention the integer part in the predicate. Can anybody tell me why is that? Do you have a guess on why that must be?
Because x is a part of all real numbers, which is z,000.
Z. Does Z represent the set of real numbers? Remember the variables, the fixed variables which represent the set of real numbers, the set of integers, and yada yada. Does Z represent the set of real numbers, or does R represent the set of real numbers?
R represents real number.
Yes. And Z represents what?
Integers.
Yes. Z represents, yeah. So you were heading in the right direction, except that Z represents the set of integers. And that is what we need, right? If Z represented, if instead of Z you had R here, it wouldn't work. It wouldn't work because you have to specify that x has to be an integer if that is the definition. If that is the definition, you have to specify that, right? So using R here wouldn't be enough. We have used Z here, however, and Z represents a set of all integers. Here we have x belongs to Z. What does that mean? It means that the domain of x is the set of integers. And that means that x is by default an integer. The domain of x is integers. What is the domain of x? Based on this, we can say that the domain of x is integers. That is, x belongs by default to the set of integer. X is an integer. That's why, because we have specified that here, that the domain of x is the set of integers, that is why we do not have to mention that again here in the predicate. If x is already an integer, we do not need to mention that in the predicate. It's a characteristic that's already fulfilled by default because we've specified that here. Okay, so that is another way of representing the same set. So whenever we represent any given set A in this manner, x such that px, we are saying that if x belongs to A, then px is true, and if px is true, then x belongs to A. That is, x belongs to A if and only if px. Okay, so you see here, if x is an element of A, then the predicate is true for x. That is, x has the characteristic. Or in other words, if x does have the characteristic, if px is true for x, then x belongs to the set A.
Ma'am, what is A? It's a set, right?
A is any set that is represented by this definition.
Okay.
Universal set. So in set theory, we always have the idea of a universal set. And all elements, all objects in this entire universe belong to the universal set. Sometimes universal sets can be specified, and sometimes they are not. An example where a universal set is specified is this one. You can have something like this. See here, in this part to the left, when we are saying that x belongs to Z, what are we saying? The domain of x is integers, the set of integers. Or the universe that x belongs to is the set of integers. Z is a part of the universal set, yes. But when we say this, we are saying that x belongs to the universe of all integers. All right? So you can have something like this specified in a problem or in a definition. The universe can be specified. If the universal set is specified, by default, we can assume that the element belongs to that universal set because all elements belong to the universal set. However, even if it's not mentioned, we have the universal set, we still have the idea of a universal set, the original idea of a universal set. How do we define a universal set? The universal set basically contains anything and everything in this entire universe. You, me, the number 6, everything. Okay, that's the universal set. So when we say that x such that px, that actually means that the set of all x belonging to the universal set such that px. Okay. Example. For example, here, let's say we have any set A represented by this definition, this set builder notation. Okay. What is it saying? X such that x is a positive integer less than 5. Here, x is a positive integer less than 5. This is the definition. This is the characteristic that x must have in order to be what? In order to be an element of A. Okay. So x is a positive integer less than 5. Obviously, that's 1, 2, 3, 4. So A has the elements 1, 2, 3, 4. We can get here based on the set builder notation. Now, this same definition. Yes.
Is it possible that x such that y is a positive integer less than 5?
Well, are you defining x then? See, like when we do set builder notation, we are defining the characteristic that this element must have. And we are representing the element with the variable x. How can you have the variable x here and use a different variable y in the predicate? You cannot. This predicate is for this specific variable, right? No, that is not following the rules of the set builder notation. All right. So you define the predicate here in terms of the variable which should represent the elements of the set. Okay. So x such that px. Right. So okay. So in this example, the definition that we have here, this can also be represented in a different manner if the universal set is specified. Let's say they specified that the universal set is the set of all integers. What if it's specified that the universal set is the set of all integers? In that case, see, if this is mentioned, in that case, we can rephrase the characteristic or the predicate and say that x is positive and less than 5. See here, the integer part is not mentioned in the definition. X is positive and less than 5. Integer part is not mentioned. Why is it not mentioned? Can anybody tell me?
Yes, because it belongs.
Because x is positive.
Ma'am, এখানে 5 দিয়েছে, so 5 টা একটা integer হবে।
And miss, it's less than 5, miss. Like there is a limit.
Yeah, x can be positive and less than 5. So what if x is 4.5? It doesn't mention that it's an integer. Sorry?
Integer
Is, as long as it is less than 5, miss, it is like applicable.
What? Come again?
Miss, as long as it is less than 5.
Yeah, but we are defining the set A, right? And what is the set A? The set A is the set of all positive integers, positive integers less than 5, right? Positive integers less than 5. So you can have a number which is positive and less than 5 and not an integer, but that will not belong to this set. In order to belong to this set, see, x has to be positive, x has to be an integer, and x has to be less than 5. Positive integer less than 5. However, the moment we specify that the universal set is the set of all integers, we can change the definition and say that x is positive and less than 5, and that will be enough. Why? Why is this definition enough? Why do we not have to mention the integer part anymore? Has the definition changed? Why? Yeah, go ahead.
Yes, because we already specified that it has to be all integers in the universal set.
How does that work? Because, yes, you're correct. Because we specified that in the universal set. But how does that work? Because all elements by default belong to the universal set, right? So whenever we specify the universal set, we can assume that by default, x belongs to this universal set. By default, x belongs to the universal set. And here we've specified that the universal set is the set of all integers. So by default, x belongs to the set of all integers. And on top of that, there are some restrictions which are defined here. X belongs to the set of integers. And on top of that, x has to be positive and less than 5. Okay. All right, makes sense? Any question?
Miss, I have a question about why do you have to apply universal set here?
We don't have to. We are saying that if it is specified. If the universal set is specified, see, here, originally the universal set was not specified. That's why we had to specify in the definition, within the definition, that x has to be positive, x has to be an integer, x has to be less than 5. If the universal set is specified, and if the universal set is specified to be the set of all integers, if that is the universal set, the set of all integers, we can say that x belongs to this set by default, right? So x will be an integer by default. So in the definition, we do not need to keep the integer part anymore. That's redundant because we already know that x is an integer based on this universal set. So if it's specified, you can rephrase it like this.
Specify positive integers, then we could only write x is less than 5, right?
Yes, very good. If instead of this, if you said, if the problem said that the universal set is the set of all positive integers, in that case, your definition, you could have just written that x is less than 5. So,
before mentioning the elements, we are just saying that the universal set is a set of positive integers. We have to mention that.
If you do, you don't have to. If you don't mention that, then you have to mention it. You have to specify it in the definition. You somehow have to define it, right? The purpose is to define this set. Either you define it here in the predicate, or first you give some definition of the universal set, and after that, you put any added restrictions that are left in the predicate.
In that case, then we can just show that A belongs to Z, right?
Sorry?
In that case, before showing the elements, we can write capital A belongs to Z, right?
A belongs to who?
Capital A, Z, I mean integers.
A doesn't belong to Z. A is a set. Z is a set of integers. A is a set itself. All right? Get this definitions clear. A here, what are we doing? We are defining A. A is a set here. This is the set builder notation that defines the set A. A does not belong to Z. You can say that A is a subset of Z. We'll get to the idea of a subset later on. But A does not belong to Z. What is Z? Z is the set of all integers. Z is a set that contains integers and integers only, not other sets. Okay? You can say that the elements of X belong to Z. You can say that X belongs to Z. You can say that X is an element of Z. But you cannot say directly something like A belongs to Z. All right? Because what is Z? Z has a fixed meaning, by the way. Z has a specific meaning. Z, R, these things. Remember from the previous sessions, they have specific meaning. Z represents the set of all integers and only integers, not other sets. So A does not belong to Z. The elements of A belong to Z. You can say that X belongs to Z if you define the elements of A using X. Is that clear?
Miss A key universal set.
No, A is not the. We are defining A. A is not the universal set. However, we're saying that it's possible that sometimes the universal set will be specified. Okay? The universal set for this set, for the set A, the universal set will be specified sometimes. If the universal set is specified in this manner, for example, if it said that the universal set for the set A is the set of all integers, then you do not really need to mention the integer part in the definition anymore, right? Because of the reasons that I've already mentioned. Yeah. Any other questions?
Yes, Miss, I have last question.
Yeah.
Miss, এখানে যদি universal set if they say everything like it's positive integer and less than 5, then তখন আমরা কি লিখবো? Like for A, what do we write then? We have nothing to
That
write.
A is equal to U. That A is the universal set.
Okay, Miss.
Right. So you will not have something like that. I mean, like, yeah. But even if you do, if the universal set is represented that manner, you could just say that A is the universal set. As simple as that.
Okay, Miss.
Or in the set builder notation, you could just write that X such that X belongs to universal set. As simple as that.
Okay, Miss.
Okay. Equality. When are two sets equal? When they have the same elements. As simple as that. Set two sets AB, they'll be equal to each other if they have the same elements. Mind you, look at the example. On the left-hand side, you have 1, 2, 3. At the right-hand side as well, you have 1, 2, 3. But do they have the same order? The elements, are they ordered in the same way? No, they are not. What does that mean? It means that order doesn't matter. Remember, back from the definition of set, order doesn't matter in set. See, that is the reason. Because order doesn't matter, because it's an unordered collection of objects, that's why, even if you change the order, it's going to be the same set. These two are equivalent to each other. Also, on top of that, see, even this set is equivalent to these two. See, there are 7 elements here. In the first glance, one of you might say that, okay, the number of elements is higher here. But no, the way we define sets, based on that definition, this set is equivalent to these two. Because if you look at the elements, we talk about the definition of the elements, not about the number of occurrences of the element. No, in case of set, the definition of the elements. But if you talk about the definition of the elements, you have 1 here, you have 2 here, you have 3 here. You have 1 here, you have 2 here, you have 3 here. 1, 2, 3 here as well. So all these sets have the same elements. So all of these sets are equal to each other. So in set, basically, we do not count repetition. We do not count duplicated member or repeated member in sets. All right? Here, 2 is repeated thrice, 3 is repeated twice, 1 is repeated twice. But still, it's the same set. Because if you think about the definition of the elements, by definition, you only have what? 2, 3, 1 here. 2, 3, 1 here, 2, 3, 1 here. Same elements. So all these sets are equal to each other. That is, in sets, You do not count duplicate members. All right. Okay, a general way to represent the equality of two sets is this. For all x, x belongs to A implies x belongs to B, and x belongs to B implies x belongs to A. All right. That is x belongs to A if and only if x belongs to B. Okay. So all the elements that are there in A will also be in B. All the elements that are there in B will also be in A. The idea of empty set. This is something that you have already actually used. This is something that you will use later on as well. The idea of empty set is a very crucial concept in solving problems or writing algorithms. When you solved some problem or wrote the code for some problem in your first programming course, if you used an empty array, that empty array originated from this concept, the concept of empty set. What is an empty set? An empty set is a set that does not contain anything, that has no elements inside it. Or a null set. The other term is a null set that has no elements inside it. Okay, it's an empty set. It's empty. There's nothing inside it. How is it represented? By two adjacent curly braces, nothing inside, nothing in the middle, or by this specific symbol here. All right. Also, mind you that the empty set is not equivalent to the set that contains an empty set. Why? Because this is truly an empty set. It does not contain anything. This, however, the one on the right-hand side, is this an empty set? The one on the right-hand side. What do you think?
No, miss. It represents an element.
No, it's not an empty set. This on the right-hand side is a set that has one element. This on the right-hand side is a set that contains the empty set. This is a set that contains the empty set. So at the end of the day, this is a set that has one element. However, this empty set does not contain anything. So the empty set is not equivalent to the set that contains an empty set. All right? Okay. So subsets. Let's talk about the idea of a subset. Two sets, A and B. If you have two sets, we can say that A is a subset of B if all the elements of A are also there in B. All right. All the elements that belong to A also belong to B. In that case, you can say that A is a subset of B. The same thing in the other direction is not necessarily going to be true. That is, it's not necessary to show that all the elements in B also belong to A. If that were the case, if all elements of A, exactly, if all elements of A belong to B and if all elements of B belong to A, then they would be equal to each other. And in that case, if they're equal to each other, you could still say that A is a subset of B. Not a proper subset, but a subset of B. You could say that B is a subset of A. You could say something like that. But by definition, the minimum requirement is that in order for A to be a subset of B, if X belongs to A, then X belongs to B. That is the minimum requirement. For all X belongs to A implies that X belongs to B. That is, all elements of A are also there in B. For example, this set 1, 2, 3, this set that has the elements 1, 2, 3 is a subset of this set. Why? Because all these elements 1, 2, 3 are here as well. This set is not a subset of this set. Why? Because the element 3 in the set on the left-hand side does not belong here. So this is not a subset of this set, right? So also something that we've already actually established, if A is a subset of B and B is a subset of A, then these two are equal to each other, right? So any questions regarding subsets? Any questions regarding any of the concepts discussed so far?
No,
It's a theory. Okay. So let's look at these two theorems that you will have to use quite a lot actually in order to come. All right. These two theorems are very important in that they are used in other concepts or proofs in other theories or in other concepts that will come later on in the course or later on in the program at any point. So what do these two theorems say? For the first one states that any set S is a subset of itself. That is, all sets are subsets of itself. It makes sense, right? If you have any set A, S, whatever, it's equal to itself, right?
Yes, ma'am.
Any given set, all sets are equal to themselves, right? In that case, if a set is equal to itself, it's also a subset of itself, obviously, right? So every set is a subset of itself. The first theorem states that every set is a subset of itself. That is, any set S is a subset of itself. If this is something that's obvious, however, we are going to prove it here and later on, so that you can use this theorem in other proofs. The second theorem states that the empty set is a subset of all sets. The empty set is a subset of all sets. That is the thing that the second theorem states. Okay, so we'll prove both of them. So any set S is a subset of itself. Let's look at the definition of a subset. This is the definition of a subset. If any set A is a subset of the set B, how do we define it? We define it as for all x, x belongs to A implies x belongs to B. Now do the same thing for S is a subset of itself. How would you define this? The first theorem here, what it states. If you wanted to define it using the definition of a subset, how would you define it? For all x, then x belongs to A and x belongs to B. The A and B would be replaced with who? With S. Exactly. So for all x, x belongs to S implies x belongs to S. This is just by definition of a subset. So this is this. All x, x belongs to S implies x belongs to S. This is what is claimed by this specific representation. This is the statement that we have to prove. This is what we have to prove. We have to prove that this implication is a tautology, that this is always true. This is what we have to prove. Clear so far?
Miss, this seems obvious, right?
This seems obvious, but we'll see how to prove it. This seems obvious. Yes, obvious. It looks like, yes, if x belongs to S, obviously x will belong to S. But how do we prove it? Using logic. That is the thing. See, so far, this is what we are practicing, right? Things that seem obvious. If things don't seem obvious, we have to find the solution, of course, and then lay out our logic. Even if things seem obvious, we still have to lay our logic. Why is it looking obvious to you? Okay, why is this obvious to you? Just lay it down. Right now, it's obvious to you based on your previous knowledge, common sense and everything. But you have to lay out your logic, because we have to learn this process in order to build algorithms later on. All right. So let's look at that. Our goal is to prove that this implication is a tautology. Yes?
Yes, miss.
Okay. So now think about implication itself. When is an implication true and when is an implication false? What are the scenarios where an implication is true? First of all, think about the truth table or the definition of an implication. When is an implication true?
Miss, if both of them are true,
Both of them true, both of them false. First one is false, second
one is true, yes.
That is, an implication will be true when the left-hand side is true and the right-hand side is true, right? That is one scenario. That the hypothesis is true and the conclusion is also true. That is one scenario, yes. And the other scenario is when the hypothesis is false. If the hypothesis is false, the implication by default becomes true. If the left-hand side is false, the implication by default becomes true. Okay. Then there's only one scenario where the implication is false, right? By that you mean there's only one possible situation where the implication will be false. Only one, right?
Yes, miss.
What is that?
You see, the left-hand side is true and the right-hand side is false.
Exactly. If the hypothesis is true, but the conclusion is false, only then the implication will be false, right? We have to show that this implication is a tautology. The other way of showing that is to show that this implication can never be false, right? The other way to show that this implication will always be true is to show that this implication will never be false. Now, in order for this to be false, what must happen? What does it mean for this implication to be false? We'll start from there. What needs to happen in order for this, what it means for this implication to be false. What it means for this implication to be false, we'll start from there and see if it leads to a contradiction or not. If it doesn't lead to a contradiction, then we can say that this will never be false. So let's see. This implication, you said that this implication will be false only and only when the left-hand side is true, but the right-hand side is false, right?
Yes, ma'am.
Okay. Okay. So if the left hand side is true, what does it mean? The left hand side is true. It means that x belongs to S. So the left hand side has to be true. X belongs to S. And then the right hand side has to be false. If the right hand side is false, what do we have on the right hand side? X belongs to S. If it has to be false, it has to be the opposite of this. What is the opposite of x belongs to S?
S does not belong.
Exactly.
X doesn't belong to X.
So if the left hand side is true, x belongs to S. If the right hand side is false, x does not belong to S. Can x belong to S and does not belong to
No,
S
miss,
be true at the
contradiction.
same time?
No, ma'am. It's a contradiction.
No, it's a contradiction. It's the same thing as saying that a propositional variable is true and false at the same time. It's not possible. This is a contradiction. X belongs to S and x does not belong to S cannot be true at the same time. So this is a contradiction. So you see, the implication being false leads to a contradiction. That is, the implication can never be false. The only possible scenario when the implication will be false leads to a contradiction. So the implication can never be false. So we can say that the implication will always be true. If the implication is always true, the implication is a tautology, which means that this definition will always be true, which means that S is a subset of itself, that every set is a subset of itself. Any set S is a subset of itself. All right? Clear so far?
Yes, ma'am.
Okay. So the second theorem, you will be able to do that very easily, actually. First, the second theorem, the empty set is a subset of S. Let's represent this using the same definition. The empty set is a subset of set. See here, A is a subset of B. B, represent that by the definition x belongs to A implies x belongs to B. Do the same thing for the second theorem. Okay? So the empty set is a subset of S. How do we define it? By the definition of a subset. This way, for all x, x belongs to the empty set implies x belongs to S. So far, this is how we define it, right? Look at the definition. Look at how we define a subset. This is how we define it, right? X belongs to the empty set implies x belongs to S. Okay, good. Now, in order to prove this theorem, what do we have to do? Again, we have to prove that this implication is a tautology, right? In order to prove that this implication is a tautology, again, think about the cases when an implication is always true. One of the cases that you mentioned was regarding the truth value of the hypothesis. What must be the truth value of the hypothesis to make sure that the implication is always true?
True or false?
True or false? I'm talking about only the hypothesis. Just based on the truth value of the hypothesis.
Oh,
Just
false.
based on the truth value of the hypothesis, can you ever say that the implication will always be true?
Yes, miss. If it is false, then we can say.
Yes, ma'am. As the null set is empty.
No,
so
let's
it-
not go there yet. But I'm just
False.
talking about the definition of implication.
Yeah, when it's false, we can.
Yes,
by
Yes,
exactly.
if it's false, we can just exactly say that it's.
Yes, exactly.
by
For an
default.
implication, exactly. For an implication, if the left-hand side is false, that is, if the hypothesis is false, by default, we can say that the implication is a tautology, right? That the implication is true if the hypothesis is false. Now, let's look at the hypothesis of this implication. What is the hypothesis of this implication? The hypothesis is x belongs to the empty set. Now, you guys tell me, is this possible?
No,
No,
X
ma'am.
belongs to empty set. Will this ever be true?
no, miss.
No.
No, by definition of an empty set, this will never be true. By definition, an empty set is what? An empty set is something that does not have any elements. So X will never belong to an empty set. This, the hypothesis, will always be false. By definition of an empty set, this will always be false. So, since the hypothesis will always be false, what can we say about the truth value of this implication, guys?
It's
True.
true by default.
It will always be true. The
Always.
hypothesis will always be false, so the implication will always be true. This is a tautology.
Ma'am,
Yeah.
I have a test at 12:30. Can I leave?
Oh, okay. Right. Yeah, let's end the session here. Unless you guys have any question, we are not going to proceed with the lecture after this point. I'm sorry, I took up a lot of time. If you guys don't have any question, you can go ahead and leave the session. All right? Okay. there was, I think somebody had a question regarding
Can
this,
I explain the last part?
the last part.
The
Do
very
you
last part.
understand that the hypothesis will always be false?
Yes, ma'am. That I understand.
Okay. Yeah. All right. Remember an implication? What happens to an implication when the hypothesis is false? The truth value of an implication.
It becomes true.
Exactly. So, if the hypothesis is false, the implication becomes true by default, right? So this implication, what can you say about this implication, this entire implication? This implication, in this
Right,
implication, yeah, if the hypothesis is false, this implication will always be true. We can see by looking at the hypothesis that the hypothesis will always be false, will always be false. So the implication will always be true. Isn't that what we set out to do? Isn't that what we had to do? We had to prove that this statement, this definition will always be true. That is what we had to prove. And that is what we just did. As simple as that. Because the hypothesis is always going to be false, this implication will always be true. And this is the implication that defines what? That defines this expression, that the empty set is a subset of S. This is the definition of this expression, right? The definition of a subset. A is a subset of B. What does that mean? For all x, if x belongs to A, then x belongs to B. Empty set is a subset of S. What does that mean? For all x, if x belongs to the empty set, then x belongs to S. Just by definition of a subset. So in order to prove this, we have to prove that this is true. And we just did that because the hypothesis will always be false. As simple as that. Make sense? Does it make sense? Guys?
Yes,
Okay, so no questions remain.
Ma'am, I have a question regarding the problem set. What are NAND and NOR?
NAND and NOR.
Yes, ma'am.
Yeah, NAND and NOR are operators, are special operators. NAND is the inverted and NOR is the inverted OR. Right?
Okay, so how do they function?
If you put a negation in
Yes.
front of OR, you have NOR. All right?
Okay.
So the truth values that you have in the truth table of an OR operation, NOR will just have the exact opposite. Similarly, for NAND, the truth value for the AND operation that you have, the AND operation, the exact opposite will be for NAND. The negation of AND is that, the negation of OR is NOR. All right?
You said if we
You can just
apply
do a
negation,
Google search for this. All right? Sorry, come again? Yeah?
Means if we apply negation in OR, it becomes AND, right?
Yeah.
So why do we say it's NOR? Like it both is true.
Both is true? What do you mean by that? Or both? I don't understand what you mean by that.
Means if we apply negation in OR operator, it becomes AND.
NOR means
NOR.
it must be NOR, right?
It becomes NOR. So the truth table of OR, what is it like? For the first combination, true, true, you have true. For the second combination, true, false, you have true. For the third combination, false, true, you have true. For the last combination, false, false, you have true. Sorry, false. For the last combination, false, false, you have false. In case of NOR, it will be the exact opposite. That is, for true, true, you will have false. For true, false, the output will be false. For false, true, the output will be false. And only for false, false, the output will be true. The opposite. Okay, the reason I didn't explain NOR and NAND in the assignment, because I assumed that you can do a simple Google search or you can ask me, I can tell you about that. If we did have anything like that in the exam, please understand that there's no need to panic. In the exam, it would have been defined. This is an assignment where you can do a bit of Google search and then find out what the definition is, or you can ask me directly like you've just done, and you can get the answer. But do we understand what NAND and NOR is?
Yes, ma'am.
Just negation on AND and negation on OR, respectively. Okay.
Miss-
So any other questions? Yeah.
Miss, the one I was confused with the De Morgan's law, Miss. If we apply negation, the OR operator becomes AND. That's where I was confused. So how can we say it's NOR?
Not exactly. Not exactly. When we apply the negation on a compound proposition, that's when the OR operator changes to AND. All right?
Okay, Miss.
Yeah, you're not directly applying the negation on the operator, right? When I say that negation on the operator, I mean negation on the truth values that you have. What does negation mean? Just reversing the truth value, right?
Yes,
That is all it means. So that's why the truth values will be reversed. But in case of De Morgan's law, however, in case of De Morgan's law, you have a compound proposition. You're applying the negation on the entire compound proposition. That's a different thing, all right?
Okay, miss. Thank you.
Okay. Any other question? All right. So just one thing that I want to mention. See, these two theorems, the proof, seem very easy and straightforward, right? Notice that we didn't even read what was going on here. We just had a discussion. We just had a discussion, established our proof for this theorem. So in the exam, when you're asked to prove something or you're asked to solve a puzzle, don't get frazzled or don't think, don't get stressed over it. All right. Just have a discussion with yourself that, okay, how would I solve this? Or how would I prove it? Or say, for example, one of you stated that this is obvious. Obviously, for all x belongs to S implies x belongs to S. But why do you think it's obvious? Try to dig into that. Why do you think it's obvious? All right. So you see, like every time you come up with a solution or you think about the solution to a puzzle or you think about the proof to some problem or whatever, write it down. Because this is something that I've heard from many students over and over again, that they struggle with writing down the logic. All right. So for that, what I'll tell you over and over again, that is that for practice the puzzles and practice the proofs for yourself, first write it down. Write down step by step. Step 1, what is it? Step 2, what is it? You don't have to be refined in the first go. First time you try, প্রথমবার যখন try করবা, don't think too much. Just think about the logic, just simply stepগুলো লিখবা without thinking, okay, প্রথমবার খুব একটা চিন্তা না করে just stepগুলো লিখবা roughly, যেটা মাথায় আসে ওটা লিখবা, just roughly একটা order follow করে, একটা excuse me, একটা certain order follow করে first time write it all down. All right, then read what you wrote and then find out if there's any step there that should be broken down or any step there যেটা আরো ডিটেইলে লেখা উচিত. Find out if there's anything between some steps that you have missed out. After identifying those, again write that. Again write down your analysis and then read that again. So by this, what happens is that the first time you write, if you write it without thinking too much, you're just putting down your raw thoughts on paper by following a certain order. Steps through order follow kore, just put down your raw thoughts and read your thoughts. Because if you keep it in your head, you're going to lose track at some point. All right. So for practice, I would recommend first step is without thinking too much about details, just jot down your ideas. Raw idea, just write it down, following a certain order. Then go through each of the steps. See, আচ্ছা কোন একটা স্টেপ কি আছে যেটা একটু ডিটেইলে বলা যায়, আর একটু ডিটেইলে ব্রেকডাউন করা যায়, then break it down. এই দুটো স্টেপের মাঝখানে এটা বলা যায়, put it there. All right, then again write the steps based on that, based on the edits that you made. এই edit গুলোর বেসিসে আবার write down the steps, go over it. And in this way, what happens is that you can lay down your logic. You yourself can identify if there's any problem in it or if there's any loophole, and if you feel that there are no loopholes, you're done. Right. So you can do something like that and send me a solution. I can give you a feedback. Or if you don't do that at all, you can try it out for your assignments or problem sets. I'll upload the solution on Friday anyway, so you can recheck once you go back there. All right. For the exam, however, I would like to remind you that you have limited amount of time. Often in this course or in many other courses I've seen as well, often what students do is they fixate on a certain problem and mess up the rest of the exam. It's very important in these courses that you segregate your time. All right. This is something very important for your first quiz, because often students, what they do is they spend too much time on one problem and they do not have enough time for the other problems. So the first thing you should do in the exam is, based on the time that you have and based on the number of problems that you have to solve, you have to distribute the amount of time. All right. Say you have total 20 minutes and 5 problems to solve. So divide it among those 5 problems. All right. And after division, do not spend more time than that. Let's say for a certain puzzle, if you have reserved only 5 minutes, do not spend more time than that. When the 5 minutes end, you're done. Whatever you did, just submit that. Move on to the next one. All right. Whatever you did within those 5 minutes, done. Move on to the next problem. All right. So do it in that manner. Even for practice as well, I would recommend doing it in that manner, okay? Because I can tell you one thing for sure, that the quiz 1, you will not get a lot of time, all right? So the first city